My name is Thomas Walek from Graz University of Technology. I work in the field of chemical engineering thermodynamics. And the title of the following talk, prepared by Michael Haring and myself, is a Gibbs-Ensemble Monte Carlo software suite implemented in Wolfram. So today we report on a Monte Carlo simulation program that was implemented entirely in the Wolfram language, and compared to conventional program packages, offers much more diverse evaluation options. For example, tracking of convergence behavior, output of intermediate results, and so on, in addition to simpler expandability. To give you a short outline of my talk, I will start with the motivation for implementing a Monte Carlo program in the Wolfram language. Then I will give a brief outline of the project in terms of the key features of the software and its typical application in my group. After that, I will present the implementation of the software to show its structure and the basic ideas applied for code design. Afterwards, I will show what we consider as the benefits of using Wolfram in contrast to conventional implementations. And finally, I will summarize my talk and give a brief outlook of the intended next steps for further development. To start with the motivation for this project, I would like to shortly explain the basic idea of Monte Carlo for those who are not quite familiar with this approach. So-called Monte Carlo experiments are a class of algorithms that use repeated random sampling to gain numerical results. So they rely on random experiments to solve problems that are actually deterministic in nature. And these methods are applied for things like numerical integration, optimization, and sampling from a probability distribution. Historically, such computer simulations started as a tool to exploit the electronic computers that had been developed during and after the Second World War, which had been designed to perform very heavy computations involved in the development of nuclear weapons and code breaking. After that, a first simulation of a liquid was carried out in 1952 by Nicholas Metropolis on the MANIAC computer at Los Alamos, which was the starting point for applications in chemical engineering and statistical physics in the field of molecular simulations. Now in our case, we apply Monte Carlo to a so-called Gibbs-Ensemble to conduct molecular simulations of phase equilibria, which means we set up two boxes, one for the vapor phase, one for the liquid phase, to simulate the boiling of a liquid in coexistence with the vapor. For that purpose, these boxes are initially filled with molecules and then undergo so-called Monte Carlo moves, which are illustrated in the figure below. So starting from initial configurations of particles in the boxes, a molecule is picked out randomly and then either moved within its own box in terms of a translation, or it is picked out from its own box and transferred to the other box, or one of the box volumes is changed. And in a similar way, additional Monte Carlo moves can be applied for more complex multi-atom molecules, like the rotation of a molecule or of its constituents, as well as bond stretching or angle bending. These Monte Carlo moves are repeatedly conducted in order to shift the system towards a minimum of its internal energy, which finally brings the system to its vapor-liquid equilibrium. And typically, the moves are organized in three phases. So there's a warm-up phase for moving the system away from its initial configuration. After that, there's an equilibration phase for bringing the system to equilibrium. And finally, a production phase during which the averages of the system properties are calculated to gain the mean bulk properties of the system. The purpose of such an organization in cycles or phases is simply to apply different strategies for trial moves during each phase in order to achieve the equilibrium more quickly overall. And the typical application of such a simulation is the determination of fluid phase properties, like saturation pressures and saturation densities for a given temperature, whereby such simulations should be seen supplementary to experiments. For example, for substances that are difficult to obtain or expensive in pure form, or for states at extremely high pressures or temperatures. Now, why choose the Wolfram language for such a simulation? Actually, the structure of these Monte Carlo algorithms, which basically consist of some nested loops, would suggest the use of Fortran or C, where these languages can play to their strength. And indeed, most open source software packages for Gibbs-Ensemble Monte Carlo simulations are actually implemented as a quite monolithic Fortran or C code, and often communicate with the user in a rudimentary way using just text files. And as a consequence, users are reluctant to change or extend such programs because it takes longer to familiarize themselves with the code than if they were to rewrite the program from scratch. And for these reasons, it was attractive for us to fully implement a Gibbs-Ensemble Monte Carlo simulation in the Wolfram language ecosystem, mainly addressing three goals. In particular, first, to provide a fairly intuitive user communication, for example, using switch statements for various procedures. Second, to ensure a simple expandability of the software for adding additional features, for example, by using a global variable environment for non-compiled functions, or the use of packages for an easy collection of additional data, or using code templates for possible code extensions. And third, a goal was to use or to make use of the diverse visualization options and evaluation options, as I will show later in my talk. To give you an outline of the project, I would like to begin with some key features of this program. It uses the optimized potential for liquid simulations force field in its all-atom version, as proposed by William Jorgensen, which considers every atom explicitly. For mixtures, there are various combining rules available, like the geometric mean or rules of the Lorentz-Berthelot type. It provides an improved insertion algorithm for binary mixtures to increase the acceptance rates of molecule transfers based on identity changes, as proposed by Professor Paniatopoulos. Furthermore, we implemented the continuous fractional component, or CFC method, developed by the working group of Thijs Vlucht, to improve insertion probabilities into the liquid at high densities. We use an auto-calibration for the number of attempted transfers per cycle to yield the required number of successful trial moves per cycle. Furthermore, the probability to choose a species for an attempted insertion can be tuned or auto-calibrated to yield an equal number of successful transfers per species. Next, the radial distribution function is determined either using a histogram-based method or a force-based method, and also the cavity correlation function is sampled, which are two very important and frequently used functions in the context of integral equation theories. And last but not least, the software permits the so-called combined analysis of results of multiple continuous simulations, which is in particular helpful in an environment with multiple distributed simulators. And I will come back to this feature a little bit later. To talk about the application of the software, This simulation suite is being used in both research and teaching. For example, we published a kind of pedagogic summary of the continuous fractional component method developed by the working group of Thijs Vlucht for improved transfer rates into liquid box at high densities. Here we provided several application examples using our software. Then in the second paper, we implemented an auto-calibration strategy for the equilibration phase in order to enter the production phase with an optimized set of trial moves. And currently, we use the software to determine radial distribution functions or pair correlation functions from the simulations as exact as possible to gain information about the local density of a fluid as a function of distance from a central molecule. Here you see such an example of a pair distribution function. So in teaching, the program represents the core of a lecture about model development and simulation, which is also a great opportunity for the developers to receive a broad feedback from students using the simulation suite, which is of course important to further improve the user-friendliness of the software. And by the way, the simulation suite is available on the notebook archive hosted by the Wolfram Foundation, where we also provide updates regularly. Next, a word on the implementation structure, which was derived from a typical simulation workflow. So accordingly, the simulation suite consists of 6 separate files with one notebook for the estimation of starting values for densities or pressures using equations of states or activity coefficient models. And we have 5 separate Wolfram language script files. So there's one for the setup of the simulation, then one for the execution on a workstation, or we have an execution handler for execution on a computer cluster with several nodes. That's because we also run the software on the Vienna Scientific Cluster, which represents an Austrian initiative on high-performance computing. Then there's one notebook for the analysis of single simulations, or a combined analysis notebook for multiple simulations. Last but not least, there's one script file for the extension of the simulation, which, for example, did not reach the equilibrium or had an insufficient number of production cycles, so that averaging was not satisfying. And all these scripts rely on the number of packages shown on the right-hand side here, providing things like thermodynamic models, for example, equations of state, flash calculations, phase diagrams, and so on, which are especially useful for the estimation of the start values. And furthermore, these packages provide the force field parameters, physical property data compiled from various data banks like the NIST data bank or the Dortmund data bank. To talk about code design, we use mainly Wolfram language scripts instead of notebooks, because these can be used both on a personal computer and the computer cluster, in particular the Vienna Scientific Cluster I talked about, and are also somewhat more resource-friendly when it comes to using GitLab for code management. At the moment, the code is a mix of compiled functions with delayed functions in order to speed up evaluation while using non-compilable data types. In these contexts, either a Wolfram virtual machine or an external C compiler can be used as target runtime. And last but not least, the listable compiler attribute is applied to facilitate the handling of non-tensor objects, as well as allowing the function to run in parallel. Finally, what is important in a distributed computing environment is the management of multiple simulators, for example, in the form of multiple virtual machines or remote computers that are available. And for such a situation, which is quite common on universities, the software is prepared to be operated from a local computer that makes the simulation setup files available to the number of remote computers via GitLab by pushing the setups from which the remote computer pulls the setups, executes the simulations, and then pushes back the results back to the Git server, from which they can be pulled by the local computer for a combined analysis of the results. Now, having explained the implementation of this Gibbs-Ensemble Monte Carlo suite, I would like to outline what we consider to be a benefit of using the Wolfram language compared to a conventional implementation, for example, in Fortran. And this benefit can best be summarized in one sentence: a picture is worth 1,000 words, which of course refers to the diverse visualization options of the Wolfram language that make the difference, and of which I would like to give you just a few examples in the following. So beginning with the estimation of start values for the simulations, these can be predicted using equations of state or activity coefficient models and can be visualized together with experimental data if available. This is illustrated here on the left-hand side in a density temperature diagram with the dew line, the critical point, and the bubble line, together with experimental data and indicating the proposed starting values for the given temperature, which are also shown here on the bottom. On the right-hand side, we have a PXY diagram, a vapor pressure diagram, where the vapor and liquid molar fractions can be estimated and proposed as starting values to the simulation, again using an equation of state to estimate bubble and dew line in the beginning. In this example, we use the Soar-Friedrich-Kwong equation of state. Now with these starting values, if you decide to use them, in the next step, the simulation can be set up, where first of all, the molecules are chosen from a mole file and can be visualized, as you see here. Then they are parameterized for the selected force field, including a check whether all necessary parameters are available concerning the bonds, the non-bonded levels, bond stretching, angle bending, and torsion. And of course, the filling of the two boxes is visualized and can be checked for plausibility, as shown here on the right-hand side. Then, having completed all the required input, a final check is provided by an overview before the setup is exported and executed as a next step. And this check includes the state variables and particle numbers for the boxes, then some simulation details like the number of cycles for warm-up, equilibration, production, then the definition of the trial moves per cycle, and further things like cutoff distances, overlap radius, and so on. Okay. During the execution by the execution script file, in our software, the convergence behavior can be tracked for warm-up, equilibration, and production phase, including a rough estimation of the remaining time, which I have to admit is really rough. And you see, this dynamic tracking is intended to look in from time to time and check whether things like the molar volume, the particle density, or the number of molecules in each box are converging, or if there are issues like oscillations or frequent phase changes in the boxes, which would suggest to abort the simulation and rerun it after adjusting some parameters. Of course, this dynamic tracking naturally costs computation time, but this can be prevented by simply minimizing the notebook and only using the dynamic tracking from time to time. Okay, once the simulation has been completed, the results are analyzed by executing the analysis script. And as a first analysis tool, the so-called Frankel plot is used. Here the fraction of the total volume taken up by a box is plotted versus the fraction of all particles in the box, where every dot represents a point sample in the simulation. Now, the closer these points cluster around the 2 points that are really the equilibrium points, the better the convergence. So the smallness of the two surfaces is a measure of good convergence. This convergence can, of course, also be tracked by monitoring the bulk properties of the system. In this example, we see the evolution of particle numbers, number densities, and volumes during the equilibration phase, which is light gray shaded, and the production phase, which is dark gray shaded. Next, the acceptance rates for the trial moves are another very important quantity that give you a feedback on the effectiveness of the trial moves. This example shows the acceptance rates of bond stretches and angle bands, where we see roughly the same number of accepted and rejected trial moves, which indicates a fairly sound distribution of these moves. What is also important are plausibility checks regarding the final particle numbers in the respective boxes, as well as the accepted insertions over the equilibration and production period. And finally, the radial distribution functions per atom or atom species pair can be checked visually, giving an impression about the structure of the vapor and liquid boxes in terms of the local density at some distance from a reference atom. Last but not least, an extension of the simulation is possible in the case that a satisfactory convergence has not been achieved, either because the simulation simply did not equilibrate or had an insufficient number of production cycles. So using the last of these 5 script files, it is possible to specify additional equilibration of production cycles, as well as adjustments of the trial move limits. And this option of an extension is a great means to avoid wasting simulation time by simply recycling existing unsatisfactory converged simulations and converging them. Now, to summarize my talk, we implemented the Monte Carlo simulation program entirely in the Wolfram language, and the resulting simulation package offers a wide range of visualization and evaluation options compared to existing packages that only communicate with the user via text files. And from our experience hitherto, this lowers the inhibition threshold for using such a program. It also contributes to a more effective workflow, even for experienced simulators. So as an outlook, we think of transferring the simulation suite to a package structure with support from Wolfram. And the next step could also be to change over to function compile and its consistent use. Once it is clear how to get over the related loss of the listable attribute and handling of non-tensor objects. And with this outlook, I would like to thank the entire development team listed here for the incredible commitment for this project over the last 5 years. And I would like to thank you for your kind attention, and I'm open to your questions. Thank you very much. There's a question, would it be possible to share the notebook? Well, you get this simulation suite, it's available on the notebook archive I hope this answers the question. The next question is, can the Gibbs-Ensemble Monte Carlo method be used for different types of optimization problems than vapor-liquid phase equilibria? Well, I think there are some applications to use two liquid boxes, but I don't really know other applications, to be honest. Then Bob asked, do you use periodic boundary conditions? Yes, as a standard measure here. And a comment from Dave: congratulations on your Wolfram Innovation Award. Is there some reason why the probability of accepting Monte Carlo move has to be an exponential function of an energy difference rather than a function like, then we have a formula. Well, this acceptance using an exponential functions is just a means that the simulation can fluctuate around the equilibrium point, I would say. So they have some kind of natural fluctuation around the equilibrium. Another comment, the molecule complex packet could be a good adjunct tool. Yes, thank you for this hint. It's on my list, and I will definitely watch this presentation also. Okay, if there are no further questions, thank you very much for your attention.